Next topic is threads. So a thread is a basic unit of CPU utilization. It comprises a thread ID. So it has a thread ID, a program counter, a register set and a stack. It has 4 things: a thread ID, a program counter, a register set and a stack. It shares with other threads belonging to the same process its code section, data section and other operating system resources such as open files and signals. So a thread shares with other threads. What all it shares? It shares its code section, its data section and other operating system resources such as open files and signals. A traditional or a heavyweight process has a single thread of control. If a process has multiple threads of control, it can perform more than one task at a time. So single threaded system, it will have a code segment, a data segment, open file system. It is a single threaded system. Multiple threaded system will have code register stack for one thread, code register stack for another also. So data and files. So you have code, data, files, register, stack. In case of a multi-threader, it can perform more than one task. Multi-thread server architecture. If a web server process is multi-thread, the server will create a separate thread that listens for the client request. When a request is made, rather than creating another process, the server will create a new thread to the service the request and resume listening for additional request. So client will send what? Request to the server and server will create a new thread as per the request. If another request is made, rather than creating another process, what will the server do? It will create a new thread to the service request and resume for additional request. So if the client is same, then what it will do? It will resume the request rather than again repeating the whole process. Multi-threaded programming benefits: responsiveness. Multi-threading in interactive application may allow a program to continue running even if a part of it is blocked or is performed a lengthy operation, thereby increasing responsiveness to the user. Resource sharing. By default, threads share common code, data and other resources which allow multiple tasks to be performed simultaneously in a single address space. Economy. Creating and managing threads and content switches between them is much faster than performing the same task for the process. And scalability. The benefits of multi-threading can be greatly increased in multiprocessor architecture when the threads will be running in parallel or different processor. Multi-threading models. There are 2 types of threads to be managed in a modern system: user threads and kernel threads. User threads are supported above the kernel without the kernel support. These are the threads that application programmers would put into the programs. Kernel threads are supported within the kernel of the OS itself. All the modern OS support kernel level threads, allowing the kernel to perform multiple simultaneous tasks and or to service multiple kernel system calls simultaneously. In a specific implementation, the user threads must be mapped to the kernel threads by using one of the following strategies: many-to-many model, one-to-many model, many-to-many, so many-to-one, many-to-many, many-to-one, many-to-many and one-to-one. So many-to-one model, many user level threads map to a single kernel thread. The entire process will block if a thread makes a blocking system call. So if the thread is making blocking call, then the entire system will block, because this one kernel is connected to many threads. Only one thread can access the kernel at a time. Multiple threads are unable to run in parallel or multiprocessor system. Examples are Solaris green threads, GNU portable threads. One-to-one model. It maps each user thread to a kernel thread. It provides more concurrency than many to one model by allowing another thread to run when a thread makes a blocking call. So suppose this thread is making a blocking call, then other threads can still run. Whereas in case of many to one, if this thread was making a blocking call, then all these will be stopped, will be blocked. So it is more efficient as compared to many to one model. One to one is more efficient as compared to many to one. It also allows multiple threads to run in parallel on multiprocessors. Drawback is each user thread requires creating the corresponding kernel thread. So each user thread has to create its corresponding kernel thread. Whereas in many to one, each user thread was not supposed to create its corresponding kernel thread. Only one kernel thread was there shared among all the user threads. Examples are Windows and Linux. Many to many model. In multiplexers, many user level threads to a small or equal number of threads allows the operating system to create a sufficient number of kernel threads. When thread performs a blocking system call, the kernel can schedule another thread for execution. So in this also, if one thread is performing a blocking system call, the kernel can schedule another thread for execution. Next is two-level model, similar to MS2M, except that it allows a user thread to be bound to the kernel thread. So one user thread can be bound to another kernel thread. Examples IRIX, HPUX, TRU64, Unix, Solaris 8 and earlier. So references, that is books which you can refer for module number 2 of operating system. William Starling's operating system internals and design principles, and you have this.